First, it's an R type, and then 0, 1, 0, 1. And notice that this is the ALU op, yellow. So these are the ALU op signals.
This how the ALU work?
That's the ALU we derived last time. Okay, you remember these were the control signals that caused it to and, add, sub, and or. All right? So that's it.
But it's hard to remember those logic terms.
Well, yeah, so, yeah.
I think that's easier than having.
No,
Oh, I was
you
saying.
don't have to remember it. I just want you to have an appreciation for that it can be derived.
Yeah.
You know, I doubt that on a test I'm going to say, show.
So is Ed.
I mean, if it was a 16-hour test, you know, whatever. You know, I'm not going to get down into the weeds like this, right? So, let's continue. Well, there we go. We're just going to permute some of the func bits and use a mux. So here we go. Here's the mux. Either it's an R type. So the R type controls either add or something else. You see it? So 0, 1, 0. That's the 3-bit. What does 0, 1, 0 correspond to?
Add.
So if it's not R type, what's it going to pick? Add. You see it? And now look at the rest of these right here. I just permute these bits. And these are the bits that I can permute. Look, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1. I just flip them around a little bit.
Hey, I ain't trying to be funny. Why is it the F2?
8 combinations?
Because I'm only going to use the func bits F3, F1, and F0 in the order F1, F3, F0. So the order in which I'm going to make them appear is 1, 3, 0. So look. 1, 3, 0. What does that correspond to? 0, 0, 0. Look.
1,
3, 0. What's that? 0, 1, 0. That means add. How about this?
1, 3, 0.
Which is, I'm sorry, let's try it
It's
again.
1, 1, 0.
It's 1, 3, 0, which is 1, 1, 0. That means subtract. And then finally, what about this? 0, 0, 1, which means
Or.
So I simply grab 3 bits from the func code, kind of twist the order around a little bit, chunk that into a mux, take the signal that means add, and chunk it into the mux, and then use R type to control it. And out pops ALU op. So now we know how to use the combination of opcode, which was R type, and func code to get ALU op. Pretty easy. All right? Now, how about R write? So, when do we write?
Well,
Whenever there's a destination register. Now, here's one of these cases. It's actually easier to think about when there's not one.
memory.
When isn't there a destination register?
Memory.
When it's a branch and a store.
Yeah, when it's stored memory,
Yes.
you know.
So if it's a branch or a store, there's no write.
Right.
Otherwise, there
Everybody
is.
else, right.
So here we go. Look, branch and store. You see it? Branch, store.
Does not right.
Does not write. So now watch. How do we do that? It's either a branch or a store. Now look at this. What is that? It's X, it's 04,
No.
X nor 03, and 02. All right? So look at it. Look at it. So, what did I say? It's X nor 04, 03. Look. Right? Where's 04 and 03?
0, 0?
It's these first two
Is it 0,
bits,
0?
right? So what does X nor mean? They're the same. Because what does X or mean? They're different.
Yeah.
So X nor means they're the same.
Right.
So if the first 2 bits are the same,
Right.
okay, then it's a branch and a store. Do you see that?
Mm-hmm.
There we go.
Oh.
First of all, it has to be a branch, and it has to be a store. So once we've decided that it's a branch or a store,
Mm-hmm.
then it's a matter of X ignoring the first two bits, and then no matter what does the third bit have to be? A 1. So watch. Now that's the condition that says not to write.
So
Agreed?
if it meets the condition, you're not to write.
Yes. So now we want the negation of that.
That mean the right.
To
That
write.
means to write, so we simply negate this and apply the De Morgan theorem. So if you negate it, all right, it's x4, x-NOR O3, and O2, not.
Right.
Okay, and if you remember De Morgan's theorem, that corresponds to O4, XOR O3, or O2, not.
Right or not to right.
There you go, and there it is. So here's the XOR that corresponds to O4, O3, right? And here's O2, not.
Okay.
And either one of those, or, bam, you do the right. Yes.
XNOR is the negation of XOR bit.
It turns out yes. It doesn't seem obvious, but it is.
It is negation of XOR bit.
It turns out that the answer is yes.
S no and S or.
X nor means,
So XOR and XNOR are kind of goofy because it goes the other way, but it's still the negation.
okay.
If you sit down and actually go through it, I know what you're thinking. I should have a not there.
That's what I was thinking too.
Because what does De Morgan say?
The opposite.
De Morgan says, flip all the variables, ands becomes ors, and ors become ands. So I know what your intuition's telling you. Oh, this should be a not, X04 not, and this should be an O3 not, right? But what's not XOR not? It's the same as, you know, if their nots are different, then it's the same as them being different.
Right.
So, yeah. And if you laid out if you took and built XNOR from primitive logic, ands, ors, and nots, and then walked through doing De Morgan on it, you would end up with an XOR gate. Strictly speaking, these would be knotted, but again, you know, because if the knots are not the same, then
Nors?
then whatever the not knots, then the not knots are different.
Dr. Morris,
Yes.
so one more time, X nor are the same.
That means they're the same, this
And-
means they're different.
Right, and so because when you do De Morgan's theory on it, it just turns on the opposite, right?
Yes, it turns out that if I take the knot of this, because remember the way De Morgan works is I'm supposed to knot this entire thing.
Right.
All right, it's worth the exercise since it's been brought up.
Did you turn that cup up again?
This is really Boolean logic, which is, you know, digital logic 101, first semester of undergraduate computer engineering. But watch. If I have O4 X NOR O3 and O2 not.
Okay.
All right. So what De Morgan's theorem says to do outside in is first negate everything and change ands to ors. So
Okay.
let's do that. So what would I get here? I would get O4 not,
Mm-hmm.
and now I'm sorry.
That's
let me
the
not do
next
that.
step.
Let's do it this way.
O3. No.
Then or O2 not.
Not.
All right, now let's look at this thing at the primitive level. How do you do XOR? X NOR, if they're the same. So let's do the truth table for that. Ready?
Mm-hmm.
A, B, C, 0, 0, 0, 1, 1, 0, 1, 1. All right? When are they the same?
First and last.
Okay, here and here. All right, so it looks like that, correct?
Right.
So what is that?
And
The truth I'm saying.
Yeah, I know it's a truth table, but what is it?
that's an and, isn't it?
X.
A, B. Right?
Right.
right?
Okay.
Or A naught, B naught. Agreed?
Agreed.
Okay, so what's the actual equation? It's A, B, A and B, right?
Right.
Or A naught
B naught.
and B naught. Now, what does the negation of that do?
It's gonna be not
Negate
A.
that whole thing.
Not. Okay. That's
Right?
the easiest way.
You
Yeah.
ready? So what do? Negate all variables, ands become ors.
Right.
And ors become ands. So what do we have here?
Not.
A naught
Not B.
or
not B naught.
and
And A
A or
or B.
Well, what is that?
That's the opposite of the first one.
All right. Now, if you take it and multiply it out, you ready?
Mhm.
Let's multiply it out. So what's A and A naught
A and A not.
is 0, right? So what's A and B naught? A, B naught. And or what's B and A naught?
B and A naught.
Which is A naught B. And what's B and B naught? 0. What's this? A and B naught or A naught and B?
That's 0.
What is it?
Oh, this is 1.
That's A XOR B.
Yeah.
All right? A XOR B. So that's what this is. The negation of that is A XOR B or not. Bam. Falls out. See it?
Mhm.
All right, so a little Boolean algebra, we get R right. All right? This one's pretty easy. How about immediate to be? All right? In our simple machine, non-R types must be I types, right? So what's M to be? Not an R type. Right? Remember we had that signal before?
R type, yeah.
So not R type must mean
Immediate.
immediate, an immediate type, and therefore bam. Put the, and what is the signal control?
Medium to base.
It's the lower
Low.
mux input, the one that's normally the B register, right? So use M to B instead of E to B. Right, and when do you do that? When it's an immediate instruction, or not an R type. All right, moving on then. Here we go. We've derived this, these, this, and this. Okay, now we have an idea on how the controller works. All right, so let's look at pipelining again. Remember, what is it? It's an implementation technique to overlap instruction execution. It has n stages in series. The output of one is the input to the next, right? Usually, you get a CPI of 1, so it either reduces the CPI and the clock cycle time, and most importantly, it's invisible to the programmer. The programmer doesn't care if it's pipeline or not. It's the same instruction set architecture to him, right? And recall this derivation. There's the speed up right there. It's the old way over the new way, okay? Because remember, instruction count's the same in both instances, so it just falls out. So this is the time to do it on the non-pipeline machine over the time to do it on the pipeline machine. What's the time to do it? This and this. And recall, we can ignore when, what was alpha? Does anybody remember?
One.
The pipeline latency. So we can ignore latency if we have a large instruction count. And so there you
Oh, because it
go.
doesn't matter.
Because yes, you know, what's 4 when, here's $1 million. Can I have 10? Can I have $10?
Yeah, sure.
No, man, I just can't spare it.
I give you 10 bucks.
Yeah, right? So what's 4 when you got, you know, what's a latency of 4 when you got 100,000 instructions? All right, here we go. You ready?
Mhm.
Uh-oh. So this is going to sort of answer your question.
What was the question again?
Can we go through the homework?
Oh,
So this is sort of going to answer the homework, albeit from the pipeline version. About the same though, right?
Mm-hmm.
we take money.
Okay, so here we go. Register to register ALU instruction. Let's see, how does it work?
Goes from the PC.
Okay, you read the PC, you read the
Yeah, I
ICAS,
get
you calculate
PC plus
PC plus 4, you read XM. Read XM into the condition, right? And you write fetch decode. Bam.
So
Right?
it,